Hello, and welcome to this video on elastic potential energy calculations for GCSE Physics and Combined Physics. And don't forget to like and subscribe. As we have seen, the elastic potential energy of an object depends on the object's spring constant and its extension or compression. The larger the spring constant, the more elastic potential energy is stored. The larger the spring constant, the stiffer the spring, and the greater the extension or compression, the more elastic potential energy is stored. The relationship between these two variables is as follows. Elastic potential energy is 0.5 times the spring constant times the extension squared, or EE equals a half KE squared. And the units are elastic potential energy, EE, are in joules, the spring constant K is in newtons per metre, and the extension E is in metres. A spring of spring constant 25 newtons per metre is extended by 20 centimetres. Calculate the energy in the elastic potential store. First we need our equation, which is EE equals a half KE squared. And once we have our equation, the next thing we need to do is check that the values are in the correct units. So centimetres needs to be converted into metres. Once we've done that, our 20 centimetres becomes 0.2 metres. Then we need to substitute the numbers from the question into the equation. So EE equals 0.5 multiplied by 25 multiplied by 0.2 squared, and only the extension is squared. And that gives our answer for elastic potential energy of 0.5 joules. A spring with an elastic potential energy store of 0.70 joules is stretched from its original length of 4 centimetres to a length of 16 centimetres. What is the spring constant of the spring? Well, first we need our equation, which is EE equals a half KE squared. Once we have our equation, we need to check that the values are in the correct units and then substitute the numbers from the question into the equation. So 4 centimetres and 16 centimetres, they're in the wrong units. They both need to be in metres. To convert them, we need to divide through by 100. So 16 centimetres becomes 0.16 and 4 centimetres becomes 0.04. Now we need to work out our extension. Our extension is the difference in our length. So we have 0.16 metres minus 0.04 metres, and that gives us our extension, which is 0.12 metres. So we can substitute that into our equation, which is 0.70, which equals 0.5, multiplied by our spring constant K, which is our unknown, multiplied by 0.12 squared. We need our spring constant to be on its own, so we need to rearrange our equation. To rearrange our equation, we need to divide through by 0.5 and by 0.12 squared. As you can see here, we've done that, and we can cancel out 0.5 divided by 0.5 and 0.12 squared divided by 0.12 squared. We can cancel that as well. And that gives us our expression here of 0.70 divided by bracket 0.5 times 0.12 squared, close bracket, and that gives us K. And if we put that into our calculator, that gives us an answer of 97.2 newtons per metre. A bungee cord with a spring constant of 15.2 newtons per metre has an elastic potential energy store of 11,000 joules. Calculate the extension of the bungee cord. Well, first we need our equation, EE equals a half KE squared, and once we have our equation, we need to substitute the numbers from the question into the equation. So we get 11,000 equals 0.5 multiplied by 15.2 multiplied by E squared, which is our unknown. E squared is our unknown, so we need to rearrange our equation to get E squared to be the subject. And to do that, we need to divide through by 0.5 and by 15.2. That cancels out, 0.5 divided by 0.5 cancels, and 15.2 divided by 15.2 also cancels. And that gives us our expression here of 11,000 divided by bracket 0.5 multiplied by 15.2, close bracket. And that gives us E squared, which is an answer of 1,447.368. However, that's not our final answer because we need E, not E squared. So now we have to do the square root to get E, and the square root of 1,447.368 gives us 38 metres. And that's the end of this video. Thank you so much for listening.